Thank you.
Okay, it's time to start today's the second session. Yeah, the first speaker is Michael Winter. His title of his talk is Sharpness in the Fuzzy World. Please start, Michael.
Thank you very much. Okay, so this presentation is again about the sharpness property or unsharpness property. I thought actually that this was covered and everything was said about this a long time ago, I would say at least 15, 20 years ago. But I encountered this problem in a slightly different version, as you will see in a minute, recently again. So, and that's what I want to be talking about. Okay, so what will I be doing? First thing is I will give you a motivation, explain exactly what it means over here, unsharpness in this fuzzy setting. Yeah. Then I will actually formally introduce what I'm using, namely those kind of categories of L-fuzzy relations and certain different kind of objects over here and constructions. And then I will talk about this fuzzy sharpness theorem, yeah, which I have proved so in order to cope with this problem. Okay, so let's start with this. Let's have a look at this, mainly at this diagram on the right-hand side. So what are we talking about? Basically, we have given those four relations, Q, R, S, and T, between those kind of objects, or if you like, if you don't want to hear any categorical terms, then see them simply as sets. And in the middle, we have this product A times B, which is a relational product, or intuitively, this is simply the set of pairs from A and B. Yeah, so given the Q and R in this diagram, we can form what's in the middle, this pairing of Q and R. So intuitively, it relates an element from C with a pair AB. Yeah, if C is related to A in the relation Q, and similar if C is related to B in the relation R, and of course very similar on the right-hand side with S and T, just with the pairing on the left-hand side instead of the right-hand side. So now the obvious, and by the way, on the left over here, you see how those constructions are actually formed in more primitive operations, where the semicolon over here is regular composition of relations, and pi and rho are simply the projection functions from the product A times B to A, respectively B. And of course, this funny hook symbol over here is the meet of two relations. Okay, so now the natural question is to ask what happens if I take this pairing followed by the co-pairing, yeah, pairing of Q and R in the middle, followed by S and T co-paired. Now, yeah, I could think about this doing it separately. Yeah, so basically going along the path on the upper way, yeah, Q then S, or going the path down there, R, then followed by T. And normally you will get that the intersection of those two paths, right, is exactly the one in the middle. Yeah. So this equation, yeah, that this is equal, yeah, is exactly what's called the sharpness problem, yeah, or the sharpness property. Yeah, it is very easy to verify this for concrete relations. So if you're taking set theoretic relations, and you can simply prove this equation very easily. There's not a challenge in doing this. Yeah? But it is not true in the abstract settings. Yeah. So if you're taking some kind of relational categories or some version of relation algebras, then you can show that this property in general is not true. And Roger Maddox provided back in '93, if I remember correctly, an example where this is not true. It's actually a strict inclusion from the left side strictly included in the right side. And he provided a model which is made out of 58 atomic relations. So of course, the whole algebra is much bigger, which shows that this in general is in the abstract setting is not true. Okay, what else can we say about this? Naya, it is also this problem, the sharpness problem is closely related to the representation problem of relation algebras or relational categories, yeah, simply because it involves basically projections and products. Okay, so Naya, when can you actually show this property also abstractly? And there have been several attempts to do this. And the easiest one is that certain relations in these equations are univalent or functional. For example, if Q and R are both functional, then also this pairing is, and then you can easily show that the equation is valid. Yeah, similar if you assume that S converse and T converse are univalent or partial functions, you can show it the same way. Yeah. So that's very, very easy and straightforward, but it doesn't cover all relations, obviously. Yeah. So just certain ones. Yeah. Then there has been approach to show this equation if or in the case that certain additional products do exist. The first proof, as far as I know, was by Hans Sierra back in the 80s, yeah, which required two additional products to exist. Yeah, that result was improved in the sense by Jules Desjardins later on, that he could show this result when there is only one additional product. So for example, if the product between C and A in this diagram exists, yeah, then the sharpness property for all relations is also valid. Yeah, all relations of this typing, of course. What else could be done? And that is a more recent result that was done by Gunder Schmidt and myself. Yeah. Basically, it says if one of the relations involved over here is between an object B and its power object, yeah, so intuitively or in the concrete set, that's simply the power set, then also sharpness holds. Yeah. Good. So yeah, that is what the general sharpness problem is about. And as I said, I think most of those kind of things have been done already a long time ago. And that is what the situation is about that. Good. So now I came up with a similar problem, yeah, in a fuzzing setting when I was doing or applying categories of fuzzy relations to concrete applications. And here we can do a very similar thing. And now you see that those pairings and co-pairings operations are all indexed by the star operation. And you see it also in the equation. It has been replaced, the meet operation, which was originally in here, by a star operation. So what is this? Now, this is, let's say, a T-norm-like operation. Yeah, and the main difference between meet is that this operation is not idempotent. Yeah, so x star x is not necessarily x. Yeah, and for meet, of course, that was the case. So x meet x is of course x. Yeah, similar. Yeah, we have a composition operation over here. Yeah, which is based on a star instead of a meet operation. And down here you see the definition of those for concrete relations. Yeah, so you take the star of two relations of the same kind. It is simply star of each entry, so that goes component-wise. And this star operation is yeah, a T-norm-like operation on the underlying lattice of truth values. Yeah, and here the composition operation. Yeah, normally this is a big join, yeah, in front of this formula. And normally with the regular relational composition, you would have over here in the middle between Q and S, you would have the meet operation, and that is here now replaced again by a star. Yeah. So, and of course, now you can ask the same question. Yeah. So if I take instead of the regular pairing and co-pairing operation and the regular composition, yeah, when I replace this by the star versions of that, yeah, I can get the same diagram and ask the same question. Yeah, is my equation over here now the star version, so to speak, of the sharpness problem, or the sharpness equation, is that valid or not? Yeah. Again, it is very easy to verify this for concrete L relations in this case. Yeah, so lattice valued relations. Yeah, and that which basically means that the idempotency of meat does not really play a role in proving this, yeah, because star again is not necessarily idempotent. Yeah, but it's also not true for all relational categories, right? Because this is just a special case of the regular unsharpness property by simply replacing, yeah, star by meat. Yeah, so of course this is also not true in general. Yeah? So, but how can we prove this equation now for the star operations, in certain settings? Yeah, now, yeah, it is. We cannot directly use the proofs for sharpness simply because the star operation, as I said already a couple of times, it doesn't satisfy as many properties. In particular, it is not idempotent, so we cannot simply apply those theorems. So we have to find a new way of proving this. Yeah. Okay, so what could be done? Yeah, we could try, of course, to generalize those theorems which we already know. Yeah. So, for example, we could start with Hans Zierer's theorem, yeah, which required 2 additional products, yeah, and use that one, yeah, in order to, or try to generalize this one to this fuzzy case. Unfortunately, yeah, this proof relies on the fact that composition with a map distributes over meat. Yeah, and this is heavily used in this theorem, yeah, or in the proof of the theorem. And the corresponding properties for this star-based composition and star is not simply not valid. It is only valid for crisp maps. Yeah, crisp means basically relations, yeah, or in this case maps, which only use as lattice values 0 and 1. Yeah, so they correspond 1-to-1 to classical maps in this case. Yeah, so a direct generalization is simply not possible, yeah, because the constructions used over there, of course, they can be applied to L-valued relations as well, but the results you're getting are maps, yeah, but not crisp maps, so you cannot use that distribution of univalent maps over star in this case, simply because it's not valid. Yeah? So I tried that, found that problem, and I was not able to modify it in a different way in order to get to a result in the fuzzy case. Yeah. So then, of course, I had a look at Joule's theorem, which only uses one additional product. And actually, to be precise, I did it the opposite way, right? Because only requiring one product is, in a sense, a little better, yeah, than requiring 2 products. Yeah. But also here, this was not possible to generalize simply because this or the proof of this theorem heavily relies on the fact that yeah, that we are using the modular inclusion, yeah, for composition and meat, and these, or the general modular inclusion, is simply also not valid for the star-based composition and star. Yeah, you will see later on there are some weaker versions available, but not the full version. Yeah, so this was also not possible. Good. Then I looked at the last theorem over here, which I mentioned earlier by Gunther Schmidt and myself. Yeah, and what I want to show you here is that this is possible to generalize. Yeah, and as a consequence of this generalization, yeah, I was able to reduce this unsharpness problem in the fuzzy case, yeah, to a regular one. Yeah, and then of course we can apply the regular sharpness properties or conditions which imply sharpness in order to get sharpness in the fuzzy case. Okay, so that's the general setting, yeah, and the problem. So now let me introduce the tools or the theories which I'm using in order to do all of this. Yeah. So the first thing is over here, the definition of a Dedekind category. Yeah, I don't want to go into details, but this is a general theory of yeah, for abstract relations. It's a categorical structure, so all of those relations are typed in a sense. Yeah, and we have yeah, the regular operations of meet, join, inclusion, smallest and greatest relation. That's under number one. And they form a completely distributive lattice. Yeah. Then we have the composition, of course, with identity, which forms the categorical structure, and the monotone operation converse, satisfying those two laws over here. And then we have number three, which is the, I would say the important one, which makes all of this a theory of relations, namely this modular inclusion. Yeah. And last but not least, we have also the residuals, are available over here. Of course, here we have only one residual, but you can define the second one by using converse. Yeah. Okay, so this is a general theory for relations, if you like, an abstract theory for relations. Yeah. So what can you do with this? You can do a lot of things. However, for L fuzzy or L valued relations, that is normally not enough, because we want to also talk about relations being crisp, meaning that they use as membership values from the lattice only the value 0 and 1, so basically correspond to classical relations, but with the interpretation 0 false and 1 being true. Yeah. Okay, so now in the Dedekind category in general, we can identify elements which basically correspond to the underlying lattice, if there is one. Yeah. And there are two ways of doing this. Ideal relations. In a matrix form, they look like this. So basically or intuitively, these are matrices where every entry, every truth value is A in this example, or the scalar relations, which are partial identities. So the identity, the diagonal, and they have the same value, in this case, again, A on the diagonal. Yeah. And of course, there are definitions, abstract definitions, which characterizes those relations. Yeah. The point is, in any Dedekind category, you can identify those kind of relations, and basically what you can do is, or how you can see those kind of relations, they are in a one-to-one correspondence, so to speak, to the truth values you are actually using in this category in terms of relations. So why I'm introducing all of this, just because they are part of the next definition, which is an arrow category, which allows you now also to talk about crispness, and this is this up arrow and down arrow operation. Intuitively, what they mean is up arrow changes the relation by modifying every truth value. So every truth value, a membership value of a pair in the relation. If it's not 0, it moves it up to 1. And down arrow does the opposite. If it's not 1, it moves it down to 0. So they are also sometimes called support and kernel of a fuzzy relation. And there are some axioms over here. I don't really want to go into details. Just to mention, you see the last one. Actually use a scalar relations. Of course, you could also use ideal relations. So that would be equivalent, and that just ensures that the crisp relations, that they are, so to speak, Boolean valued, meaning yes, a true and a false value being used for those ones only. Okay, so that are arrow categories. Now we can actually talk about L relations. So L valued relations. But we need a little bit more. We need our extra operation star. So in this abstract setting, and that's what a fuzzy category is. So what you see over here in the beginning is basically the number 1 and 2 is that star is something like a meet, except that it is not necessarily idempotent. Then it says number 3, it says that meet and star behave the same. If one of the component is actually a crisp relation, or if you want to talk in terms of truth values, that star treats 0 and 1 like meet, so like a regular, like an AND operation. Good. So then the additional axiom over here for converse. Then we have a group basically saying the same thing about, or a similar thing about, the star-based composition. You see these are very similar, except that the star-based composition is, of course, not commutative in general. Yeah. And last but not least, we have two additional axioms, namely this exchange law. Yeah. um, you see for yeah. Or let me put it that way, in terms, this is a generalization of the corresponding one for meat and composition, but for meat, it would, on composition, there would only be one relation on the left-hand side of the composition over here. There would not be Q star R, there would be just one Q. Yeah. And down here, you see three versions of the modular inclusion. Yeah. And modular inclusion is treated over here by replacing some of those operations in the modular inclusion, composition and meat, by the corresponding star version. Yeah, the general one, yeah, where everything has been replaced by stars, is not valid. Yeah, except you're splitting. You see this in number 3. You're splitting the relation Q, which is normally at this place instead of P star Q. You split this up into two relations, yeah, combined by star. Yeah. So again, what I'm want to point out over here, the general modular inclusion for star and star-based composition is not valid. There are 3 weaker versions which are valid. And actually, I did this, I think, last Realmex. Yeah. Okay, good. So now we have to talk about products as well. So what is a product in this setting? Yeah, we have an object a times b together with those two relations pi and rho going from a times b to a, respectively b, and they satisfy those well-known axioms over here, except in the fuzzy setting, they are also required to be crisp. Yeah, that is just an additional requirement because we don't want informing a pair of crisp values that the result is all of a sudden not crisp anymore. Yeah, that's the reason for having this additional axiom. And of course, if you are not considering L relations, yeah, then in a sense you consider all relations to be crisp. It's not a restriction in that sense. Yeah. Here's a picture in terms of Boolean matrices, yeah, of the projections. Yeah. So you see over here, the pi has 1, 2, 3, 4, 5, 6 rows. Yeah. So the product I'm talking about over here is from 2 elements times 3 elements, and you see the first 3 pairs. Yeah, they have all the first element from the 2-elemented set as the first component. Yeah, that's why we have the one over here, the ones over here, and the second 3 pairs have the second element as the first component, and similar with the projection. Yeah, so this is how they look like if you print them as Boolean matrices. The second construction I need over here is, yeah, so to speak, an abstract version of a power set, but of course now in a fuzzy setting. Yeah, so if you have seen those kind of constructions earlier, especially by Rudolf Berghammer or Gunther Schmidt, yeah, you will recognize that's basically the same construction, except yeah, that you have around the symmetric quotient over here, yeah, which is just a version combining both residuals. You have those arrows over here attached to it. Yeah, and why is that? Now this has simply something to do with fuzzy sets and fuzzy power sets. Yeah, because what we want in this case is we want that this power set or this P of A in the concrete case, yeah, is the set of all fuzzy subsets of A. Yeah, and in that sense, or in that case, yeah, this element relation, which is defined over here, epsilon, yeah, is not extensional anymore. Yeah, so it's simply not the case, yeah, that two fuzzy sets are yeah, fuzzy equal. I have to say that in that way. Yeah, if and only if they contain the same elements with the same degrees. And I show you why that is. Here is again a picture of this epsilon relation in terms of a matrix. Yeah, the lattice I'm using over here is simply the linear lattice 0, A1. Yeah, from below. So 0 smallest, 1 greatest, and A some value in the middle. Yeah, and we are considering over here the element relation on yeah, between two elements, a set of two elements, and its power set. And if you want to read this column-wise. Yeah, so the first column, 0, 0, yeah, corresponds to the empty subset. Yeah, both elements are definitely not in. Yeah, the second set over here, the column 0a, yeah, corresponds to the set which doesn't contain the first element and contains the second element with degree a. So it's a fuzzy subset, and so on and so forth. Yeah. And what I said about the extensionality of this is, yeah, so what I'm saying is symmetric quotient of epsilon with epsilon itself, yeah, is not necessarily the identity, yeah, because those two, that doesn't work over here. The second column and the third column, yeah, those two sets, yeah, they are actually equivalent with a degree of A. And you can see this if you take those two columns and intersect every value in the column by A, yeah, you get exactly the same result. Yeah, so that is why those two sets are equivalent up to degree A. Yeah, so in this matrix sig epsilon epsilon, you would get an A outside of the diagonal. Yeah, so it's not the identity. Yeah, but yeah, what this equation says over here is, yeah, that those sets which are completely the same, yeah, meaning, yeah, they have the same values with the same membership values, yeah, that these are only, yeah, every set with itself. Okay, so that was a long talking about this construction. The other construction down here basically, yes? Okay, the second construction basically transforms transforms a relation into a corresponding map. Okay, so I have to speed up a little bit. So here's the theorem again, yeah, namely showing that can be shown for concrete relations very quickly, easily. Yeah, this is the generalization of the theorem by Günter Schmidt and myself to the fuzzy case. Yeah, so if one of the relations is a function followed by some relation, yeah, which goes in parallel with a univalent relation down here, then you can show sharpness. Yeah, and that's now being used or can be applied to a particular case where one of the objects is a power set, because there you have always actually even a function parallel to any relation. Yeah, which is this is simply the relation sending an element x to the singleton set containing it. Yeah, and now you can, if you apply this, you can show that this kind of sharpness, where we have two epsilon relations up here in the front, yeah, that this is valid. Yeah, and now you can do the general theorem by simply taking this diagram, yeah, replacing it by this more complicated diagram. The left-hand side collapsed to the triangle, and the right-hand side collapsed to that triangle because of that theorem. And now in the middle, yeah, you have just crisp relations, yeah, and meaning you have a general or an original sharpness problem in the middle. Yeah. So in general, you get this the theorem over here saying that if you have a bunch of additional products, 4 of them, yeah, then and for the product in the middle, yeah, there is a sharpness, yeah, then you get the fuzzy sharpness. And as a particular corollary out of this, if you have all relational products and powers, which are used over here, yeah, then also fuzzy sharpness holds automatically, yeah, because relational products, having all relational products, gives you the regular sharpness property by Jules de Janet's theorem, for example, or theorem. Okay, that is what I wanted to talk about. Yeah, thank you very much.
Thank you.